Hello everyone and welcome back to Math Made Easy. In our previous lectures, we studied three important direct methods for solving systems of linear equations. We learned the Gauss Elimination method, the Gauss-Jordan Elimination method, and the LU Decomposition method. All of these methods belongs to the category of direct methods because they produce the exact solution in a finite number of computational steps, provided there are no rounding errors. However, let us consider a very practical engineering problem that involves 10,000 equations and 10,000 unknowns. Would direct methods still be efficient? Although they are mathematically accurate, the computational cost and memory requirements become extremely large for such massive systems. In such situations, engineers and scientists often prefer another class of numerical techniques known as iterative methods. So instead of obtaining the exact solution immediately, iterative methods begin with an initial approximation and then improve that approximation stepwise until it becomes sufficiently close to the actual solution. So today we will study the Jacobi Iterative Method, one of the most simplest and widely known iterative methods for solving systems of linear equations. We will understand the mathematical idea behind the method, derive the iteration formulas, and discuss the conditions under which the method converges and solve a complete numerical example. So before learning the Jacobi method, let's just first understand the difference between the direct methods and the iterative methods. The direct methods compute the solution in a very finite sequence of operations. And the examples includes whether this Gauss elimination, Gauss-Jordan elimination, and the LU decomposition method. These methods are efficient for small and medium-sized systems. However, for very large systems, direct methods require significant computational time and memory. And this is where these iterative methods become very useful. An iterative method doesn't compute the exact solution immediately. Instead, it starts with an initial guess and repeatedly improves it. Each new approximation is closer to this true value than the previous one. And this process continues until the desired accuracy is achieved. So suppose we have the following system of equations as this 10x plus y plus z equals to 12, 2x plus 10y plus z equals to 13, 2x plus 2y plus 10z equals to 14. Instead of eliminating the variables, let's just rewrite each equation by isolating one variable. From the very first equation, we get this x equals to 12 minus y minus z divided by 10. From the second one, we get this y equals to 13 minus twice of x minus z divided by 10. And from the third equation, we get this z equals to 14 minus 2x minus 2y divided by 10. So notice something interesting. Each variable is here expressed in terms of other variables. If we start with approximate values for x, y, and z, we can repeatedly substitute these values into the equations to obtain better approximation. And this simple idea forms the basis of the Jacobi iterative method. So if we consider the very general system as this a11x1 plus a12x2 plus up to a1nxn equals to b1, a21x1 plus a22x2 plus and up to plus a2nxn equals to b2. And hence an1x1 plus an2x2 plus up to annxn equals to bn. Now solve each equation for its diagonal variable. We get this x1 as 1 by a11 multiplied by b1 minus summation a1j xj, where j is not equals to 1. Similarly, this x2 becomes 1 by a22 into b2 minus summation a2j xj, where j is not equals to 2. Continuing this way, we get this xn equals to 1 by ann into bn minus summation where j is not equals to n anj xj. Now introduce the iterations here. The Jacobi iteration formula becomes xi k plus 1 equals to 1 by aii into bi minus summation aij xjk, where j is not equals to I. Now notice something very important, like every new approximation is calculated only the values obtained in the previous iteration. Unlike the Gauss Elimination method, which we will study next, the Jacobi method never uses newly computed values within the same iterations. So a natural question arises like, will the Jacobi method always converges? Answer is no. The most important sufficient condition for the convergence is diagonal dominance. A matrix is said to be strictly diagonally dominant if for every row this mod of aii is greater than summation of mod aij, where j is not equals to I. In simpler words, the absolute value of the diagonal element should be greater than the sum of the absolute values of all the other elements in the same row. So for example, if I have this matrix as example as this 10, 1, 1, 2, 10, 1, 2, 2, 10. Now checking each row, we get this 10 is greater than 1 plus 1. This 10 is greater than here 2 plus 1. 10 is greater than here 2 plus 2. Hence, the matrix is diagonal dominant and the Jacobi method is expected to converge. Now that we have derived the Jacobi iteration formula, let's just summarize the complete algorithm. Whenever we solve a problem using the Jacobi method, need to follow the following steps as just write the equation of the linear equations, check whether the coefficient matrix is strictly diagonally dominant, and if not, rearrange the equations if possible. And then rewrite each equation by isolating one variable and write the expression for x, y, and z, or the given unknown variables. So now choosing an initial approximation as 0 and using these values to compute this x1, y1, and z1, and repeat the whole process until the desired accuracy is achieved. Now we need to solve the following system of equation. Now let's just solve the following system of equation using the Jacobi Iterative Method, where we have given this 10x plus y plus z equals to 12, 2x plus 10y plus z equals to 13, this 2x plus 2y plus 10z equals to 14. Taking the initial approximation as 0, so this x0 becomes 0, y0 is 0, and z0 is 0. Now checking the diagonal dominance, as is row 1 having this 10 is greater than 1 plus 1. In row 2, we get this 10 is greater than 2 plus 1. And in row 3, this 10 is greater than 2 plus 2. Hence the system is diagonally dominant and therefore the Jacobi method is expected to converge. Now rewriting the equations, from the very first equation we get this x equals to 12 minus y minus z whole divided by 10. And from the second one, we get this y as 13 minus 2x minus z whole divided by 10. And from the third, we get this z equals to 14 minus 2x minus 2y divided by 10. Now, these are called the Jacobi iteration equations. We have already chosen the initial approximation. So now just to substitute only the values from the 0th iteration. So we get this x1 as 12 minus 0 divided by 10 equals to 1.2. Similarly, we get this y1 as 13 minus 0 divided by 10 equals to 1.3. And hence, the z1 becomes 14 minus 0 divided by 10 equals to 1.4. Now notice something very important, like while calculating this y1, we didn't use x1. We still used x0. Similarly, while calculating the z1, we used x0 and y0. And this is a defining characteristic of the Jacobi method. Every new approximation uses only the values from the previous iteration only. Now with the second iteration, we got this x2 as 12 minus 1.3 minus 1.4 whole divided by 10 equals to 0.93. This y2 becomes 13 minus twice of 1.2 minus 1.4 whole divided by 10 equals to 0.92. And finally, we get this z2 as 14 minus twice of 1.2 minus twice of 1.3. and whole divided by 10, which we get 0.90. And with the third iterations, we get this x3 as 12 minus 0.92 minus 0.9 divided by 10 equals to 1.018. This y3 becomes 13 minus twice of 0.93 minus 0.9 whole divided by 10 equals to 1.024. And in this z3 becomes 14 minus twice of 0.93 minus twice of 0.92 whole divided by 10, we get this 1.030. And with the fourth iteration, we got this x4 as 0.995, y4 as 0.993, z4 as 0.992. And with the fifth iteration, we get this x5 equals to 1.0015. And y5 is 1.0018. And z5 becomes 1.0024. Since the values have stabilized up to 3 decimal places, so you just need to stop the iterations now. Now observe the sequence carefully. The approximation first overshoot the solution, then undershoot it, and then gradually settle around the exact answer. This oscillator behavior is common in many iterative methods and indicates that the sequence is converging. So the exact solution of the system becomes is x equals to 1, y1 and z1. Now notice how each iteration brings us closer to the solution. So a practical question now arises, when should we stop the iterations? The most common stopping criteria is this maximum part of xk plus 1 minus xk, this mod value of yk plus 1 minus yk, or zk plus 1 minus zk value, which should be less than epsilon, where this epsilon is the prescribed tolerance. Another commonly used criteria is to stop when the values remain unchanged up to the required number of decimal places. Now notice that the first three methods are direct methods. They aim to compute the solution in a finite sequence of operations. Jacobi method belongs to a completely different category. It gradually approaches the solution through the successive approximation, and the difference is the fundamental distinction between the direct and the iterative methods. So suppose while calculating the y1, the value of x1 has already been computed. The Jacobi method ignores this new value and still uses this x0. So, however, the Gauss-Seidel method immediately uses the updated value. Because of this, the Gauss-Seidel method generally converges faster. And this is the most important difference between these two methods and is frequently asked in exams. Although the Jacobi method appears theoretical, but it has many practical applications. It is widely used in electrical circuits analysis or heat transfer, fluid mechanics or finite element analysis or finite difference methods, image processing, and machine learning optimization. Whenever very large system of linear equations arises, iterative methods such as Jacobi becomes extremely useful. So today we introduce the Jacobi Iterative Method, our first iterative technique for solving systems of linear equations. We learned how iterative methods differ from different direct methods, derive the Jacobi iteration formulas, and discuss the convergence criteria based on diagonal dominance, and solved a complete numerical example using a successive approximation. We also explored the advantages, limitations, applications, and the practical significance of the method in scientific computing and engineering. And one important concept to remember is that the Jacobi method always computes every new approximation using the values from the previous iterations. This characteristic makes the simple method highly suitable for parallel computations, although it generally converges more slowly than some other iterative methods. In the next lecture, we'll study the Gauss Iterative Method. We'll discover how a simple modification using the newly computed values immediately within the same iterations can significantly improve the speed of convergence. We will derive the Gauss iteration formulas, solve the detailed numerical examples, and compare it with the Jacobi method and understand why it is often preferred in practical computations. Thank you for watching, and if you found this lecture helpful, please like the video, share it with your classmates, and subscribe to Math Made Easy for the complete numerical analysis course. And I'll see you in the next lecture.